Hello friends, today's question. An ideal gas enclosed in a vertical cylindrical container sports a freely moving piston of mass m. The piston and the cylinder have equal cross-sectional area A. When the piston is in equilibrium, the volume of the gas is V naught and the pressure is P naught. The piston is slightly displaced from the equilibrium position and released. Assuming the system is completely isolated from the surrounding, the piston executes a SHM with the frequency of. In this case, we are going to use the equilibrium condition as well as the adiabatic relation of the gas and try to find out what will be the frequency of the SHM. So we are going to start with the equilibrium condition. So under equilibrium, condition, we can write the equation that P naught A will be equal to M multiplied by G. We have P naught, it is given as the pressure of the gas when the entire system is in equilibrium. Pressure of the gas, A is the cross-sectional area, A is the cross-section area, and capital M is the mass of the piston, and obviously G is the acceleration due to gravity. And in this case we have to remember it is said that system is completely isolated, so we can say this is a adiabatic process. So we can use the adiabatic relationship of the gas. So we can say adiabatic relation for the gas, and we know that pressure volume raised to power gamma is equal to constant, where this gamma is the adiabatic index. And it will be equal to Cp by Cv. Now we assume that there is small displacement of x in the piston, small displacement of x in piston, and in this case we assume that the volume is changed from V naught to V naught plus Ax. We say that volume changes from V naught to V naught plus Ax. Therefore, we can write that the pressure change which can be approximately written as P is approximately P naught, and this becomes V naught, and we have V naught plus Ax whole raised to power gamma. And for small value of x, we can just expand it. So we can say for small value of x, the expression can be written as P is approximately P naught 1 minus gamma Ax upon V naught. Therefore, the pressure deviation which we can represent as delta P will be equal to minus gamma P naught Ax divided by V naught. Now the net force of piston will be due to this pressure deviation. You say that net force on the piston is due to pressure deviation. And this net force, if represented as F, can be written as delta P multiplied by A. We substitute the value of delta P, we get this as minus gamma P naught A square x upon V naught. Now this force is going to act as a restoring force. This force acts as a restoring force, and which can be further written as that our F will be equal to minus K effective multiplied by X. And this K effective constant, if we equate these two equations, we can say, let us call this equation number 1, equation number 2. So we say using equation 1 and 2, using equation 1 and 2, we get K effective X is equal to minus gamma P naught Ax upon V naught. Here X cancel with X, and we get that our K effective will be equal to gamma P naught A square upon V naught. And the frequency of SHM, or rather we can say angular frequency of SHM, angular frequency of SHM, that is of omega, it can be given as square root of K effective divided by capital M. We substitute value of K effective, we get that our omega is equal to gamma P naught A square divided by M multiplied by V naught and its square root. So therefore, the frequency of oscillation, that is F, will be equal to omega upon 2 pi. So this comes 1 upon 2 pi square root of gamma P naught A square upon M multiplied by V naught. So this is the frequency of oscillation for the SHM. And the option, we can just check it out. Option number C is the correct one. Option C is correct. C is This completes the question. Thank you.